Okay, in this video we'll be going through the 2016 Level 3 Mechanics, bro? Come on now. Okay, in this video we'll be going through the 2016 Level 3 Waves Exam. The way I recommend you watch this video is to pause the video before every question, attempt the question yourself. Once you've completed the question or get stuck, unpause the video and see how I go about getting the answer. Okay, question 1. A pan flute is a musical instrument made of a set of pipes that are closed at one end. Maria produces different frequency notes by blowing air across the top of the pipes. Maria is producing the fundamental frequency, which is the first harmonic, in one pipe. On the diagram below, draw the standing wave that Maria is producing in the pipe. Label the displacement nodes and antinodes. Okay, so we have a case where we have a pipe closed at one end and open at the other. We know that this means that we have a node over here and an antinode at this end. And we also know if we have this situation, the first harmonic, the length of the pipe is equal to 1/4 wavelength. And so we can simply draw 1/4 of a wavelength like so. There we go. Maria blows across one pipe and the fundamental frequency of 350 Hz is produced. A second pipe produces a fundamental frequency of 395 Hz. Explain which pipe is longer. Okay, so we know from this equation right here that our length is directly proportional to the wavelength. Now, due to V is equal to F lambda, and therefore lambda is equal to V over F, we can see that the wavelength is inversely proportional to the frequency. And so as you can see, if the length increases, the wavelength will also increase, and if the wavelength increases, then the frequency will decrease. And so therefore the 350 Hz pipe has the lower frequency out of 350 and 395, and therefore the 350 Hz pipe is the longest. Maria blows across one of her pipes and it produces a third harmonic with the frequency of 762 Hz. At the same time, her friend Sophie blows across a similar pipe that produces a third harmonic. They both hear a sound of 764 Hz, which is the average of the two frequencies. The sound varies in loudness at a frequency of 4 Hz. State the name of this phenomenon and explain how it causes Maria to hear a variation in loudness. Okay, so this phenomenon is called beats. Beats occur when there are two different sounds of similar frequencies. Now if you think about this from a fixed point, aka where Maria is standing, due to the fact that the frequencies are slightly different, they will come constantly in and out of phase. So if you think about frequencies that are the same, they will always be in phase at a certain point, right? But if they are slightly different, they will come in and out of phase. And that's the fundamental idea behind beats. So when the frequencies are in phase, they will constructively interfere, therefore producing a loud sound. And when they are out of phase, they will destructively interfere, therefore producing a quiet sound. And so as they constantly come in and out of phase, they will constantly produce a loud, quiet, loud, quiet, loud, quiet, loud, quiet. And so that creates a beating frequency. And again, you can write that in lovely words. Calculate the length of Sophie's pipe. Okay, so the frequency produced by Maria's pipe is 762 Hz, and we can call that F1. Now because the beat frequency is 4 Hz, we know that Sophie's pipe produces a frequency of 766 Hz. And we can call that F2. The reason why we know it's 766 and not 758, right, how I got 758 is this minus 4, which is 758. So how I know it's 766, meaning going up rather than going down, is because we know that the average frequency is 764. And so if we do some math, 762 plus 766 all over 2 is equal to 764. And so that's how I got it. Right, it would be impossible to replace this with 758 and then get a higher frequency than this. That makes no sense. Right, we know that this is the third harmonic, right, because it's given up here. Sophie blows across a pipe that produces the third harmonic. We know that V is equal to F lambda, and therefore lambda is equal to V over F. We know the speed of sound in this case is 343 meters per second, because it's given all the way up here. And obviously we know our frequency at the third harmonic is 766. So simply plugging in those numbers, we get 343 all over 766, and we get a wavelength of 0.4477 meters. Now, because we know this is the third harmonic and we have a pipe as so, with a closed end and an open end, we know that the third harmonic is going to be 3 all over 4 lambda. And now plugging in our numbers, 3 over 4 times 0.4477 is equal to our length, and this gives a length of 0.3358 meters. There we go. Okay, question 2. Mike is flying his radio-controlled plane. The plane flies towards him at a constant speed and then away from him at a constant acceleration. As shown in the diagram, the plane is producing a frequency of 185 Hz. Assume the speed of sound in air is 343 meters per second. Describe and explain the frequency of sound that Mike hears when the plane is at position X. Okay, so at position X, which is right here, the plane is moving towards him at a constant speed, and therefore this is our regular Doppler explanation. We have a plane, which we can put as a dot, and as it's moving towards it, it catches up to its previously emitted wavefronts, which gives the wavefronts a shape as so. And as you can see, the wavefronts in front of the plane are bunched up because it catches up to its previously emitted wavefront. And what this results in is Mike over here perceiving shorter wavelengths, right? And therefore, as the velocity of sound is constant, due to v is equal to f lambda, if Mike perceives a decrease in wavelength, the frequency that he observes is going to increase. Describe the frequency of sound hears when the plane is at position y. Okay, so at position y, that is directly on Mike himself. And as the plane is producing 185 Hz, Mike is going to hear 185 Hz. And so he will hear the true frequency, which is 185 Hz. There we go. Describe and explain the frequency of sound that Mike hears as the plane gradually accelerates away from him. Okay, so this is our Doppler situation with a slight twist. If we just imagine that the plane is not gradually accelerating away, and it's just going away at a constant speed, we know that it's going to be the reverse scenario of what we see over here. If it's going away at a constant speed, that means Mike is over here now, and his perceived wavelength is going to increase, and therefore, as velocity is constant due to v is equal to f lambda, the frequency that he perceives is going to be decreased compared to the true frequency. However, as the plane is now accelerating away from him, the plane's velocity is going to increase, and therefore if we do our scenario again where we have our... If the plane is getting faster and faster, it's going to catch up to its previously emitted wavefronts even quicker after every passing second, right? And so what that means is that if this gets more bunched up, this is going to get more separated. And so the wavelength that he perceives is going to gradually increase. And so what that means is the frequency that he hears is going to gradually decrease. And this is what students kind of get mixed up with, because they think, oh, he's already hearing a decrease in frequency. That is true. The true frequency is 185 Hz. And then Mike will hear a frequency of 150 Hz due to the Doppler shift. However, as the plane is accelerating away, this number is going to gradually decrease to 145, to 140, and then 130, then 110, right? It's going to gradually decrease. So he hears a drop due to the Doppler, and even then, that frequency is decreasing. If you like to explain things using equations, we can even look at our Doppler equation, where we have the source frequency times the wave velocity. Wave velocity? Yeah. And then VW minus, and then VW plus VS, right? Because we're going away, so we use plus. We know that acceleration is equal to velocity over time, and so if our acceleration is increasing, our velocity is going to increase, obviously, and therefore our source velocity will always increase. And because our source frequency is constant and our velocity of our wave is constant, if the velocity of our source continues to increase, then our perceived frequency will continue to decrease. And you need to explain that in words. Calculate the speed of the plane when the sound waves being produced behind it have a wavelength of 2 meters. Okay, so we know our Doppler equation, frequency of the source times the velocity of the wave all over velocity of the wave plus velocity of the source, because in this scenario the plane is moving away from us. Now we know that v is equal to f lambda, and therefore f is equal to v all over lambda. And so we can use this equation to substitute for our f prime, and we get VW all over our lambda prime. The reason why we use lambda prime is because this is our perceived change in wavelength, and also the reason why we use VW is because this is the velocity of the wave in this case. And so that's equal to our source frequency times our VW all over VW plus Vs. Now because we have VW on both sides, we can divide by VW on both sides, and that will cancel out. And we get 1 over lambda prime is equal to Fs all over VW plus Vs. Now, I don't really like this 1 over lambda situation, so I can take the inverse of both sides, and we get lambda prime is equal to VW plus Vs all over Fs, right, our source frequency. And so we know our source frequency is equal to 185 Hz. We know that because that's given in our question. We know the velocity of our wave is 343 meters per second, again because that's the speed of sound. And in this question, we're trying to calculate when the wavelength is 2 meters. And so our lambda prime is equal to 2 meters. And the question tells us to calculate the speed of the plane, which is our Vs, so that is our unknown. And so simply we just have to rearrange for Vs. We can times by our source frequency on both sides, and we get lambda prime times Fs is equal to VW plus Vs. And now we can minus by VW on both sides, and we get lambda prime times Fs minus VW is equal to our source velocity. And therefore, 2 times 185 minus 343 is equal to our source velocity, and this gives us a value of 27 meters per second. There we go. Okay, question 3. Moana is doing an experiment in the laboratory. She shines a laser beam at a double slit and observes the interference pattern on a screen. The diagram below shows the experiment. Moana measures the distance between the adjacent bright spot, which are maxima, and find they are 0.01 meters apart. The slits are 1.28 times 10 to the negative 4 meters apart, and the screen is 2.1 meters from the slits. Show that the wavelength of the laser light is 6.1 times 10 to the 7 meters. So for this question, we can use our n lambda is equal to dx all over L. We know our x is the spacing between the maxima. We know our d is the slit separation, and our L is the distance from the screen. So if we set n is equal to 1, our lambda is going to be dx over L, and now plugging in our numbers, 1.28 times 10 to the negative 4, times our slit separation, which is 0.01, all over our distance L, which is 2.1 meters. And this gives a wavelength of 6.1 times 10 to the negative 7 meters. And as you can see, that is the value that we're trying to find. Moana replaces the double slit with a diffraction grating in the same position. The diffraction grating has 500 lines per millimeter. Calculate the angle between the central antinodal line and the first antinodal line. So 500 lines per millimeter is equal to 500 times 10 to the 3 lines per meter. And therefore our d is equal to 1 over 500 times 10 to the 3, which can simplify to 2 times 10 to the negative 6 meters, right? And so our trusty equation, n lambda is equal to d sine theta. We want to find the angle, so we can rearrange for sine theta, and so we get n lambda over d is equal to sine theta. Now we want to find the angle by itself, not sine of the angle, so we can take the inverse sine of this whole thing, like so. And now plugging in our numbers, we know that n is equal to 1 because we're trying to find the angle between the central node, which is n is equal to 0, and the first antinode, which is n is equal to 1. So 1 times our wavelength, which we found in the previous question was 6.1 times 10 to the negative 7, all over our d, which we just found was 2 times 10 to the negative 6, which gives an angle of 17.75 degrees. There we go. Now if you look at the answer schedule gives an answer of 17.5 degrees. Now I am fairly certain this is wrong, because if you plug in the numbers that the answer schedule gives, it also gives my answers. So I'm pretty sure the answer schedule is wrong, but it's close enough. Explain what would happen to the distance between the bright spots on the screen if the laser source is changed to one with a shorter wavelength. So we know that in lambda is equal to d sine theta, right? Our trusty old equation. So if n remains constant, and d also remains constant because it's the same diffraction grading, the only thing that we need to worry about is lambda and sine theta. So if lambda decreases, that means sine theta must also decrease, and therefore the antinodes will get closer together. And you can write that down. Moana then shines white light through a diffraction grating. The pattern she sees is shown below. Explain the pattern that Moana observes. In your explanation, you should include why the center of the pattern is white, why there is a colored spectrum on either side, and why there are dark regions between the white and colored regions. So as we know, white light contains all the wavelengths of visible light. So as white light goes through and passes through our diffraction grating, those wavelengths are going to spread out over this 180-degree area. And as we also know that each slit in this diffraction grating acts as a point source for these wavelengths, right? And so if there are multiple point sources of these wavelengths, those wavelengths are going to interfere with each other, and those dark regions are when all the wavelengths meet out of phase and therefore destructively interfere, thus leading to a dark spot, or a node. Now, as for the colored regions on either side, as we know, n lambda is equal to d sine theta. As we know, the different colors on the visible spectrum have different wavelengths. So for example, red has the longest wavelength, and therefore we can say it has the greatest wavelength. And violet has the shortest wavelength. And so therefore, due to this equation, and for the same reasons as this question above, red light is going to diffract more, and so its angle of diffraction is going to be greater than violet. And so we can see that in our picture. We can see red right over here, and we can see that it's diffracting more than violet, which is right over here. Now, as for the central band, which is white instead of a spectrum of colors, we know that the central antinode, which is n is equal to 0, we know that there is 0 path difference at this point. And what that means is all the wavelengths of white light meet at that single point in phase, thus constructively interfering. And because white light is made of all the visible wavelengths, and all the visible wavelengths construct at that point, it's obviously going to result in a white antinode, as we see. So there was a lot of information in that question, but you can rewind and write that in lovely words. And with that, we are done.